welcome to part one of my three-part video series on how to find the inverse of a function algebraically. In each one of these videos I'm going to go through three examples. I'm going to give you a function and I'm going to show you how to calculate its inverse. And before you watch this, you probably want to start with my video that's called What's an Inverse? And then go into maybe a graphical approach to inverses, and then watch this video. In order to understand what we're doing here, it's probably helpful to have some sort of a foundation. So let's begin. In number one, our job is to, of course, find this function's inverse. That's the notation we use, right? It's a little -1 exponent. We don't say -1 though, we just say f inverse. And to do that, to find that thing, right, it's a function that, as we said in the previous video, it sort of undoes, or it's the function that sort of undoes the original function, or it's kind of like the opposite of it. And if you're looking for more of an explanation on that, go to the video that's called What's an Inverse. But for this video, since it's probably going to be long to begin with, let's just get right into it. Here's the process. To find the inverse of f of x, I'm going to just replace f of x with y. And then I'm going to switch x and y. Right? That has a very, very sort of obvious connection to what we talked about in the previous two videos. We're always switching x and y. And then from here, we're going to solve for y. So maybe we write these steps down here. Switch x and y and solve for y. Alright, those are the two steps really to finding the inverse. So let's get 3 over here to the left. We're going to add 3 to both sides. We're trying to get y by itself. And we're going to divide everything by 6. Alright, and once we solved for y, what I want you to do is just replace that y with the notation f inverse. And we can rewrite this, it's like 1/6 x plus 3 over 6, which is 1/2. Right? That is the same thing, just kind of a different way of writing it. Or if you wanted to, you can write it like x over 6 plus 1/2. Right? It's exactly the same thing. Totally up to you. Or you can just leave it like this. It's totally fine. So I claim that those two are inverses of each other. All right, and there are a couple ways to check this. There's of course the graphing method, and you would take this and put it into your graphing calculator and see if it's symmetrical. It must be symmetrical, as I mentioned previously, across that line. In other words, the function and its inverse must sort of reflect over y equals x. I'm not going to do that right now, though. That's more of a graphing approach. What we're looking for here is an algebraic approach. So there are two ways. I'll show you one. I'll show you both, actually. Let's do this one. So if we take something like f of 2, 6 times 2 minus 3, so that's 12 minus 3, so that's 9. F of 2 is 9. And in the previous video, what's an inverse, you saw that, well, that must mean that f inverse of 9 better be 2. Well, let's check. So now let's plug in 9 up here. So we get 9 plus 3 over 6. 9 plus 3 is 12, over 6 is 2. It's confirmed. So algebraically, we can see that f of x and f inverse sort of undo each other. They're kind of like functions that sort of undo each other, right? The other way of checking this, I told you there were two ways. You can compose f with its inverse, and when you compose f with its inverse, you should get x. So let's try that. If you're a little rusty on your composite functions, your compositions, you can go to my video that I just made about 2 weeks ago, composite functions, and it'll tell you what this notation is here, this little circle thing. But basically, we're just kind of embedding the two functions together. We're sort of nesting them together. So let me get this function down here. I'm going to make it a little bit smaller, and I'm just going to bring it down here. And my inverse, if I remember correctly, was, let's see, it was x plus 3 over 6. All right, so let's compose these two together. When you compose a function with its inverse, you should always get x. Let's see. So I'm going to put f inverse inside of f. So I'm going to rewrite f of x, and instead of putting an x, I'm going to put the inverse. All right, this comes from 6x minus 3. 6x minus 3. And instead of the x, I'm putting the inverse right in there. All right, that's how we compose functions. So now let's just kind of simplify it, clean it up a little bit. You see a 6 on top and a 6 on bottom, they cancel. So that leaves us with x plus 3 minus 3. Well, what do you know? X plus 0, which is just x. When that happens, when the function and its inverse compose with one another, you should get x. And vice versa. When you compose the other way, and as we've mentioned before, composing functions is not commutative. It's not a commutative operation. So traditionally, most times, this and this will not yield the same thing. But for inverses, it should. Let's check. So now let's write the inverse first. So it's x plus 3 over 6. But instead of writing x, we're going to write our original function. 6x minus 3 plus 3 over 6. So we're trying to simplify this. Negative 3 and 3 is 0, so 6x over 6. And what do you know? The 6's cancel out, and we're left with just x. So as you can see, when you compose a function with its inverse either way, in either direction, you get the same thing, x. All right, number 2. If you feel confident, give this one a shot. Pause it and see if you can find the inverse of this function. Step 1, turn f of x into y. Step 2, switch them. Step 3, solve for y. To undo a square root, we want to square both sides. And we're going to subtract 2. We don't want to write y, we want to write f inverse. Alright, so my claim is that this function and this function are inverses of each other. Alright, so let's go to, let's go to the graph this time. We go to a graph, and we'll see if this makes some sort of sense here. Oops. So we have the square root of x plus 2. I'll put that in y sub 1, and in y sub 2 I'll put x squared minus 2. Alright. So we can see that we have, a graph, and it's probably, when you graph these things in your TI 83 or 4, you probably want to be in zoom 5, which zooms to a square. Makes our intervals a little bit nicer to see. We have an interesting thing here because our original function has a range restriction, right? None of the range values can be negative. All right, so all my range values must be non-negative, 0 included. All right, so this is not a very good representation of a function, that has an inverse, that is a function. And if you look at my other video, you can see that to see whether functions have inverses that are functions, we're talking about functions being 1-to-1, which is a horizontal line test. So we can make this inverse a function by restricting its range, which is kind of interesting. But we can also check this algebraically. Let's just pick a random number. Let's say, if we're trying to pick maybe f of 14. What's f of 14? Well, it's the square root of 14 plus 2. So that's a square root of 16. 4 times 4 is 16. So f of 14 is 4. My claim is that when I plug that in to my inverse, when I plug this value into my inverse, I should get 14. So let's check. 4 squared minus 2, 16 minus 2. And sure enough, it is 14. So there's a nice connection there. We're making connections hopefully visually and algebraically. Last one, and then we'll wrap this video up. So here we go. Let's go y equals. Let me just kind of jump the gun here. Let's just switch it right off the bat. I think we're ready for that. Just switch them right off the bat and solve for y. So I'm going to add 5. I'm going to multiply by 2. Remember, when you do that, you have to put the left side in parentheses. Distribute that if you want to. To get rid of a square, you have to square root. But remember, when you take the square root of both sides, you have to take the principal and the negative root, positive and negative root. So that's my inverse, right? I'm not going to write y, I'm going to write f inverse. All right, and you can confirm both algebraically and graphically if you'd like. There is one more here. I just remembered I have 4. So let's do this one. Let's switch them right away. So 3y minus 1, 5y plus 2. Pause it and see if you can get y by itself. It's a little bit tricky here. To solve this, I'm going to say, all right, x is actually x over 1. Let's cross multiply. Right, this is just a proportion, so let's just do one of these. So we have 5y plus 2 in parentheses, x outside the parentheses equals 3y minus 1 times 1. And let's just multiply, distribute this thing in, 5xy plus 2x. And we're trying to get y by itself, so let's move all the y terms over to the left, all the terms that have y in them, I should say. And we'll move the x terms over here. Just kind of doing some algebra here. I'm trying to group all the terms that have y's in them over on the left, because I want to factor that out. Right, y is in both of those terms. If I divide it out, I get this. And now I just want to divide out by that binomial. So these, of course, cancel out, and we get our inverse is equal to negative 2x minus 1 over 5x minus 3. And this one might be good to graph. Let's check this one. What was my original function? Let me kind of bring that down here so I have them together. Let's see if these two sort of fit our graph. And I have to make this a little bit smaller. Here we go. Alright, so I'm going to go into my graphing calculator and I'm going to clear out the old stuff. So I'm going to put, let's see, 3x minus 1 divided by, notice I'm using my parentheses here for my binomials. So there's y sub 1. And let's do, oops, forgot my parenthesis. Quantity negative 2x minus 1 divided by quantity 5x minus 3. So when I graph these, I should see that they are symmetrical across the line y equals x. Let's see if it's easy to see. Might not be for this one. Yeah, it's not a very good look at it. Maybe we'll zoom in. Zoom to, press enter. So the graph with its inverse should be symmetrical across the line y equals x. Not super easy to see here, but if we go in and we put in the line y equals x, and maybe I'll make it sort of look a little bit different. Maybe I'll make the inverse look a little different by bolding it. Maybe we can see now that this is the function graphing now, the inverse is darker, and they should both reflect across that line. So if we were to fold our screen, right down this line right here, we should see that both the inverse and its functions sort of meet up with each other. And I think you could probably see that. But anyway, that was part one, right? A huge a huge algebraic approach here. And the next two videos, we're just going to kind of hammer home some different examples and hopefully solidify this concept for you. So look forward to part 2 and 3 coming up in a little bit. Thanks for watching, and make sure you hit subscribe so you don't miss any.